Greetings everyone. Today we are going to study an important topic in coordination chemistry, that is concerning the bonding in coordination compounds. So today we will see the valence bond theory to uh, explain the bonding in coordination compounds. So we have seen Werner when he first proposed the structure of molecules that are coordination compounds, said some postulates like metal is there, a ligand is there, and then bond between them is directional in space, etc. But he was unable to specifically say about the bonding in coordination compounds. Like some of the peculiar characteristics of coordination compounds was not explained on the basis of Werner's theory. For example, why only certain elements that are transition elements are showing this property of forming coordination compounds. And also why the directionality is there in the case of coordinate bonds. And also some characteristic properties like magnetic, optic, like we said that the coordination compounds are highly colored. Why this happens is not explained by Werner. So to explain this peculiar characteristic, certain theories were formulated like valence band theory, BBT, crystal field theory, ligand field theory, molecular orbital theory, etc. So all these theories have some differences and try to explain the properties that are specific to coordinate bonds or coordination complexes. So in this class, we are going to see this valence bond theory, abbreviated as VBT. So the main point in valence bond theory is that a metal, when under a ligand comes in the vicinity of a metal atom, or the ligand comes to the metal, comes near the metal atom, metal atoms atomic orbitals can undergo hybridization. Hybridization that we have studied. Hybridization. What is hybridization? It is mixing of atomic orbitals to give uh, equal number of um, hybridized orbitals that are same in energy and all the properties, in the energy, in shape, and everything. So this mixing can happen by with the penultimate d shell also. So NS, NP, NT orbitals can hybridize to give hybridized orbitals. Also, n-1d, ns, and np orbitals can also hybridize to give hybridized orbitals. N means the outermost one. And these hybridized orbitals are those which is going to overlap with the ligand orbit. How they are going to accept the lone pair of electrons or electron pairs from ligand, and thereby this metal ligand bond is formed. So the directionality of the metal ligand bond is successfully explained by this method. So we'll see how the hybridization happens, how many hybridized orbitals, and based on that, what is the geometry of this molecules, etc. First, consider coordination number 4. For coordination number 4, there is two types of hybridization possible, that is sp3 and dsp2. sp3 means this ns and np, the outermost s shell and p shell is being hybridized to give 4 sp3 hybridized orbitals, and the shape that is specific to sp3 hybridization is tetrahedron. That means a metal is there and 4 ligands are approaching it from the 4 corners of a tetrahedron. And then the next possibility is dsp2, where the inner d orbital is being used for hybridization, and the geometry corresponding to it is square planar, like this. Metal is here and ligands are occupying the position like this, where all these metals and ligands are in the same plane, and the ligands are at the corners of a square containing the metal. And then coordination number 5 has the hybridization sp3d, and the shape is trigonal bipyramidal. That is given here. Metal is there, and in that plane, 3 ligands are coming the corners of a triangle, and 2 ligands are at above and below the plane of the metal. And for coordination number 6, 2 hybridizations are there. The geometry of both is octahedral, even if it is taking the inner d orbitals or outer d orbitals. The hybridization can be of 2 types, sp3d2, d2sp3. The geometry is octahedral. That geometry is given here. Metal and 4 ligands are in the square that is in the same plane of metal, and 2 are above, one each are above and below the plane of the metal. Now we will see some examples for valence bond theory explanations. Consider this complex CONH3 6 times the whole charge is 3 plus. Here the charge of cobalt is 3 plus. So cobalt is the central metal ion here. So we will consider the atomic orbitals of that atom. So cobalt is a cobalt 3 plus has this configuration on 3D. That is, there are 6 electrons in the d orbitals. 4s is vacant, 4p is vacant. So how many ligands are there? 6 ligands are there. So hybridization should be either d2sp3 or sp3d2. So the geometry will be octahedral. So here, how hybridization happens like this. Here, this one electron from this shell will go and pair up with this electron, and this will go and pair up with this electron. So this happens. So what will be there? This is a vacant d orbital. This is a vacant orbital, and this 2 d orbitals and 1 s and 4p, 3p orbitals are going to get hybridized. This is the hybridization. Then this d2 sp3. So since the inner d orbital is used for hybridization, we will write the name of that orbital first, d2 sp3 hybridization. So these are the d2 sp3 hybridized orbital. Here, what happens? The 6 pairs of electrons from 6 ammonia molecule will come and occupy this orbitals in the case of this complex. So these type of complexes are known as inner orbital complexes, which the inner orbital is used for the hybridization. They're also known as low spin complexes or spin paired complexes, because there is no unpaired electrons in the whole structure of this complex. Therefore, they are known as low spin or spin paired complex. Spin paired means there's the electrons are all paired. Now coming to the other type of hybridization, for the case of the ligand is changed and F minus ions are the ligands. Then what happens is that here this pairing is not happening. Therefore, but 6 fluoride ions are there, so the hybridization should be hybridization should be 6. So the hybridization here happening is 4 sp3d2 sp3d sp3d2 hybridization. So here on this sp3d2 hybridized orbitals, the 6 pairs of electrons of 6 minus signs are coming. And this kind of molecules are known as outer orbital complexes because the outer d orbital is being used for hybridization. It's also known as high spin or spin free complex because of this single occupied single occupied electrons. This is known as this type of complex is known as high spin complexes. Now we will see the valence bond theory explanation in the case of compounds having 4 ligands. There are 4 ligands. What are the possibility? What are the possibility of hybridization? They are sp3 as well as dsp2. sp3 geometry is tetrahedral and dsp2 geometry is square planar. So consider this complex where nickel is the central metal atom and 4 chlorides are the ligands. So nickel 2 plus ion has this electronic configuration that is 3d8. So here says the hybridization is happening between the s and 3p orbitals. That is sp3 is the hybridization and the geometry is tetrahedral. So in this 4 sp3 hybridized orbitals, the 4 pairs of electrons from the Cl minus is coming and occupying. Here there are 2 unpaired electrons, therefore it is having paramagnetic characteristics. So when the ligand is changed to Cn minus, what happens is that the pairing of electrons happening in the 3d orbit, and there is an available vacant d orbital that is inner to the s and p orbital. So the hybridization here is dsp2, d and sp2. sp3 is not used, sp3 is not used, sp2 is used. So in these 4 dsp2 hybridized orbitals, 4 pairs of electrons from Cn minus is coming and getting occupied. So here this is a low spin complex because there is no unpaired electrons in the case of the whole complex's electronic configuration. Here the geometry is square planar because the hybridization is dsp2. Okay, with this, we are coming to the end of this topic. In the next class, we will see some magnetic properties of coordination complexes based on this valence bond theory. And we will see certain drawbacks of this valence bond theory that we will see in another class. Thank you for watching. If you have any doubts, don't hesitate to ask in the comment section.